Okay, let's continue on with our next example. When a 43.5 gram sample of lithium nitrate dissolves in 62.3 grams of in a calorimeter, the temperature drops from 27.2 to 13.2. What is the change in enthalpy for this process in kilojoules? If the reaction is simply lithium nitrate dissolving into water to form lithium ions and nitrate ions. So this is an example of when you would use a coffee cup calorimeter. As such, you would have water, and then you would dissolve the lithium nitrate ion into ions, lithium +1 and nitrate -1. This is where the system and the surroundings becomes important, because the system is actually the ionic bond between lithium and nitrate. The surroundings are going to be the water. So what's going to happen is the temperature of the water goes down because the lithium nitrate bond is absorbing energy from the water. So remember, we talked about system, and everything else is the surroundings. So what's going to happen is the system, which is the lithium nitrate, is going to absorb energy. So this is an endothermic process, not a chemical reaction, but an endothermic process. We're going to use MCAT again. So we've got Q equals mass, specific heat capacity, and change in temperature as it refers to the water. And we have Q equals MCAT as it refers to the salt, the lithium nitrate. So these are equal and opposite. The salt is going to gain energy and the water is going to lose energy. We don't care about the negative signs or the positive signs. We just need to refer to one as being negative and one as being positive to refer to one is losing energy, one is gaining energy. So we've got all the information we need to solve for delta H or Q. In this case, delta H and Q are the same thing. We use them all the time interchangeably because as long as the pressure is the same, which a coffee cup calorimeter is a constant pressure device because it's just a coffee cup, we could not manipulate the pressure in it. So Q and delta H are the same thing for our purposes. So we're going to deal with what we know everything about, which is the water. So 62.3 grams of water, specific heat 4.184 joules per gram degrees Celsius, and then change in temperature, which is 27.2 minus 13.2 degrees Celsius. So if you notice, the grams cancel and the degrees Celsius cancel, and I'm going to be left with units of joules in my answer, which we will have to change to kilojoules because that's what it's asking. The answer we get is 3,649 joules, which is equal to 3.65 kilojoules, like such. But most of these times, these problems want it, because it doesn't matter, it's a 43.5 gram sample of lithium. Most of the time, they're going to ask you for a general answer, which is kilojoules per mole, not kilojoules per this specific question. So we have 3.65 kilojoules per 43.5 grams of lithium nitrate. That's actually the correct way to describe this answer. If we want a more general form, we'll change grams of lithium nitrate 2 moles of lithium nitrate. And lithium nitrate you'll add up off the periodic table of the elements, which is 1 lithium, 1 nitrogen, and 3 oxygens, and I'll get 68.951. Really, the answer you get would be kilojoules per mole, because grams will cancel out, and that's a more general form and a more useful bit of information about lithium nitrate. And you end up getting 5.783 sig figs kilojoules per mole. Just to clarify, 5.78 kilojoules per mole like that is exactly the same thing, just a little bit different way to report it, but means the same thing. Just easier to write in a document. Okay, let's do number 4. If 50 grams of water at 25 degrees Celsius is mixed with 100 grams of water at 110 degrees Celsius in an insulated container, what will be the temperature of the mixture? Well, I'm going to explain something to you because this might be a multiple choice question on the AP exam. So you have 50 grams of water in one container at 25 degrees Celsius. And you have 100 grams of water at 110 degrees Celsius. So if this is a multiple choice question, we know that when we mix them together, the temperature is going to be somewhere between 25 and 110. There is more 110 degree water, so the temperature will be closer to 110 degrees Celsius. So if you had process of elimination in a multiple choice question, you might not have to do this whole problem. So if it was equal amounts of 25 degree and 110 degree water, which is a difference of 85, if you had equal parts, then the temperature would be 25 plus 42.5. So you could look at the multiple choice. One might tell you something less than 25. One might tell you something right in the middle of 25 and 110, which is 67.5. You know, neither of those are reasonable. And then one might tell you 110, one might tell you greater than 110. We know that it's going to be somewhere between 67.5 and 110 degrees Celsius. So let's go over the concept of this. Well, the enthalpy or heat of the cold water is going to be equal and opposite to the heat lost by the hot water. So the cold water is going to gain energy and the hot water is going to lose energy. And this will happen until the temperature of the water is the same. So we've got MCAT for the cold water is equal to MCAT for the hot water. Remember, we don't care about the negatives and positive signs. We already know that the cold water is going to gain energy or have positive enthalpy. The warm water is going to lose energy. So let's replace what we do know. We know that the mass of the cold water is 50 grams. I didn't write this problem. I would have put more sig figs. So let's not worry about sig figs for this problem. The heat capacity of water, and then the change in temperature is going to be whatever that final temperature is minus 25. The mass of the hot water is 100 grams times the specific heat capacity of water and times 110 minus the final temperature. Notice we flip those around to account for the negative sign. Also, these are both water, so their specific heat capacities are going to be the same. So they will cancel out of the equation. So you get 50 times the final temperature minus 1250. I'm just expanding this. So 1250 is 50 times 25. And then I get 11,000 minus 100 times the final temperature. So we're going to rearrange to solve for the final temperature. And we're going to get 150 TF is equal to 12250. My final answer is 81.66666, so on and so forth. I'm not going to worry about sig figs, but we're going to round to a final temperature of 81.7 degrees Celsius, which is between 67 and 110, just like we thought. Let's do another calorimeter problem. It says calorimeter, it's burned in a calorimeter, so the system is going to be the inside. Now, when I say box, I mean this is a metal container. It is a hard metal container. It's got to be able to withstand pressure. Both of these are hard metal containers. This is the system inside of here, and it is an exothermic process because combustion of a hydrocarbon is always exothermic. So the system's going to lose energy, and the surroundings are going to gain it. I'm going to burn it, and then we measure the amount of water, amount of energy the water absorbs. Remember, we're talking about propane, so the coefficient for propane has to remain 1. So I'm going to balance this like such. And I'm going to calculate the change in temperature before I start this time. 95.4 minus 11.2. And I get 84.2 degrees Celsius. So the energy lost by the propane is going to be equal and opposite to the energy gained by the water. Let's write what we do know. So we've got mass of propane change in temperature and the mass of the water. We also know the specific heat capacity of water, which is a constant that will always be given to us. So we're going to do delta H, which is equal to the heat is going to be MCAT. Matter whether we use the water or the propane, we would get the same answer, but we don't know the specific heat capacity of propane, so we're going to use water at 3104 grams, 4.184 joules per gram degree Celsius, times the change in temperature, which is 84.2 degrees Celsius. So in my calculator, 3104 times 4.184 times 84.2 gives me an answer of, we expect it to be high because propane gives off a lot of energy, and the temperature change was great for a very large amount, in a very large amount of water. This is joules, so when I answer in kilojoules and I'll round to 3 sig figs, I get 1093 kilojoules. And that's my final answer. Okay, nope, just noticed that I actually rounded wrong. So it's 1094 kilojoules. Sorry about that. So what if they asked us, which would be very likely that they would ask us to find how many kilojoules per mole of propane, which is what we would use that mass of propane for. So I'm going to use my raw answer here. This is how many kilojoules I have. And I'm going to put that I have 23.5 grams of propane. And I need grams to cancel from the bottom, so I'll put it on the top. And I need to change it to moles of propane. 1 mole, we're going to add up 3 carbons plus 8 hydrogens for 44.094. And now I'll multiply across the top and divide by the bottom, 23.5. And I get an answer of 2051.808. But I want to round that to 4 sig figs again. So 2052 kilojoules per mole. So here's some examples of some MCAT problems and different things you could see from math problems before we get to Hess's law, which is next.